Okay, so we left off last time on Unit 9, reading in the airline data set, which was this big government data set of airline delays and takeoff times and those sorts of things. Okay, so any questions picking up from there? Okay, so I said I'm not going to do this in real time for hopefully fairly obvious reasons. But I read in the airline data set from a set of CSVs and then loaded it in using the FF and FF-based packages. And then as a result and then I used FFsave to basically save it back out in a binary format that's saved in a more compressed way than the original CSVs. So the other advantage of that is we can then load that back in. That doesn't read it into memory, but that sets things up in some fashion such that it's then available for us to work with. So when I actually did the FF load on this data set, it was only taking, it looks like, about 2 or 3 minutes to get it back and accessible to us. Okay. Okay, so I did the FF load. It gives me a little bit of information about where some temporary files are being stored, so it's good to be aware of where those are and make sure there's enough disk space wherever it is that that's being stored. For some reason it's leaving off the slash here, but I'm pretty sure this is /temp. And then we can go through and try and look at the data and get a sense of it and start thinking about fitting statistical models and whatnot, and we'll do a little bit of that, nothing particularly in depth here. But I can, for example, just print out one of the variable names, and it shows me a little bit about what's in that variable, and it says, oh, this is stored as apparently this is stored as a factor because it's giving me back the different levels. And so this is the destination airport. These are the 3-letter airport codes for the different records. And I guess I probably should have said each record in the database is basically one flight, when it took off, where it was going to, where it was coming from, how long the delay was on arrival, how long the delay was in the departure, those sorts of things. I can also do it's always a good idea to do some basic querying just to make sure, just as a reality check, to make sure that the data you've read in match your understanding of what they should look like. So one check here that we could do is, I've used the table function, except there's a version for these FF data frames. So one thing to be aware of here that actually tripped me up briefly was that table itself is not a generic function. So even though I can't do just table on this object because it's not going to go through the S3 method dispatching mechanism, because table itself is not a generic method. So I have to explicitly call table.ff to make sure that I'm actually running the FF version of the table function. When I first did this, I didn't realize that. I left off the FF, and it was just taking inordinately long because it was trying to actually use table, and table is expecting a regular data frame, not an FF data frame. So there was an implicit coercion going on behind the scenes where the whole big FF data frame was getting converted and presumably then trying to load that onto memory. So that didn't work very well. But then we see that the results make some sense. The airports with the most departures were O'Hare and Chicago, Atlanta, Dallas-Fort Worth, LAX, et cetera, et cetera. So at least reassuring that we haven't done something totally wrong in terms of reading the data in and what the data look like. So then, of course, if we're going to think about fitting any sort of statistical model, we want to try and get some sense of what are the possible values of the outcome. Start to think about whether these might be normally distributed and whether the data are of a fashion such that the residuals might be normally distributed if we did fit models. So this is just the first 50 values of the departure delay values, and we can say, okay, these are probably in minutes. Interesting that there are some that are minus negative values, so presumably that means these are flights that left before they were supposed to leave. Most of those, it look like, are relatively not very much before. Looks like the formatting of this got messed up a little bit. This is just the formatting that R's print function is using. And if we look at the min and the max, again, I'm making sure to call the FF versions of min and max. You can see that there are some weird values in the data set. So presumably this flight did not leave minus 1,400 minutes before it was scheduled to leave, but there's some, there's some coding error with the data. And this may very well be a real value that the flight left 2,600 minutes after it was supposed to leave. But we might want to think about long tails if we start thinking about fitting models to these data, for example. Just a quick point that sort of not surprisingly, given the fact that we're dealing with a big data set, if you just do an assignment, you're not actually doing a full copy. And if you did really want to make a full copy, you have to use the clone function. OK, so any questions so far? All right, so then I loaded in the big GLM, big LM package. And FF base provides a big glm.ffdf that behind the scenes uses this big LM package. So I'm just going to fit some toy models here. Don't take this as an applied statistics course. I'm not doing any very careful checking of whether or not this makes sense as a model, but I just want to illustrate that we can do these sorts of things. So first I take a subset of the data where the departure delays, I'm cutting off the right tail and I'm cutting off the left tail just so I don't have values that are extremely large. So this is not a very good workaround for dealing with a long tail, but hopefully you guys will give me a little bit of a pass here. And anything where there's a missing value for the departure delay. And then I just, for example, as an initial model, I'm just fitting a linear model where I regress the departure delay on the year in which the flight occurred. This could be an initial assessment whether or not there seems to be some trend in whether departure delays are increasing or decreasing. So you can think about all sorts of, I'm sure if we had a discussion of this, that we could come up with about 75 different reasons why this might not be a good model. But be that as it may, it took about 800 seconds for it to run this individual linear regression. And then I also ran one where I had the departure delay be a function of both the year and the month and the day of the week to try and get some sense, are there systematic effects of what time of the season is it and what day of the week it is. So you might expect there are going to be fairly strong effects of whether it's summer during the summer travel season or winter, whether it's on a Monday versus on a Saturday, those sorts of things that many of you have experienced in real life. And so this is the result from that initial first regression. You notice it prints out the sample size here, which is, as we've seen, pretty big. And we can see that indeed there does seem to be, at least in this linear fit, who knows whether or not there are nonlinear effects going on as a function of time. We get this as the coefficient. Prints back a 95% confidence interval, standard error, p-value, which in this case is not, may or may not, I'm not sure if this is because it's cutting off after a certain number of digits or if this is actually down near the limit of how small a number the machine can represent. But in any case, presumably quite a small p-value. Okay, any questions about that? And then if we fit if you remember, I had specified that month and day of week were factors, so we should get back a different effect for each level of the factor, the usual sort of thing when we're basically fitting an ANOVA as a regression, or thinking of a regression and ANOVA as being equivalent, as all being in the class of linear models. So here we do also get estimates that are very precise. We've got confidence intervals that are between 2.36 and 2.41, things like that. Again, the p-values are obviously excluding zero as effects in all of these cases. And we can see whether or not these things make sense. More delays in December and January during the holiday travel season, more delays in the summer. I'm now forgetting exactly how these were coded. Oh, that's interesting. It left out month 10 as the baseline level for the month, maybe because it's somehow doing it alphabetically based on what the first one is. So we might want to figure out how to change that if we didn't like that. And I'm guessing that day one is actually, let's see, can we make sense of this? So looks like the largest delays are on this day, so I think this is probably Friday. We could go and check to see if that were the case. I think it was Friday, Thursday, Wednesday, Tuesday, and that would mean that So that sort of makes good sense. Tuesdays and Saturdays is not having delays as long on average. Okay, so I don't have too much more to say about that, but we can fit these large models. We can fit ANOVA type models. We can fit regressions, etc. And as you would guess from the fact that this was called, one of these things was called big GLM, we can also fit GLMs as well. And then the other thing I just want to point out, this is a little bit of an editorial comment, an example with an editorial comment lying behind it. I basically just generated data where there was a relatively small effect of one variable on the outcome. So I'm generating y's that are normally distributed with a mean of 0.001 times some x1 and no effect of x2 and x3. But I'm going to fit a model where I regress y on x1, x2, and x3. So this is basically me generating simulated data under this scheme. So basically I'm going to okay, so that's the model that I'm generating from, and then I'm fitting and estimating the coefficients of the model. So I can go ahead and I write that out as CSV in chunks, chunk by chunk, and then I read that back in as one of these FFDFs. And if I go ahead and fit that model, so here's where I'm fitting the model, regressing on x1, x2, and x3. If I actually compute what the R² of this model is, basically I can explain essentially 0% of the variation in y with x1 and x2 and x3, even though y is a function of x1. Okay. And if I fit this model, then here's the result I get. I get an estimate of the coefficient that is indeed right around 0.001. The 95% confidence interval is reasonably tight around that. The p-value is highly significant, 1 times 10 to the minus 6, it looks like here, right? So, and yet, if I actually estimate, what the R² from this regression is, and that's, this line of code up here, I'm getting, I didn't do it on all of the observations, I just did on a chunk of the observations. I'm getting that the R² is essentially 0. Okay, so I just basically did this to illustrate, remind you that particularly when we have large data sets, we can get a highly significant result that in practical, in its practical consequences may be essentially meaningless. When you're fitting these models, pay attention to practical implications and not just statistical significance. Okay, any questions about that? Okay, so I have a few more things to mention in the big data context. So one is sparsity. So oftentimes in statistical statistical modeling, we can represent things using sparse matrices because a lot of the values are zeros. And if we can do that, we're often going to be able to save a lot of space in representing the matrix, and we can often save a lot of time in actually doing the computations. And the reason is, if we know that some chunk of the matrix is zeros, there's no reason we actually need to explicitly store those zeros. We can just represent the fact that there are zeros, we can just basically store the values that are non-zeros, and all of the missing places we know then are zeros. And if we're doing a big matrix, say matrix multiplication, and most of these values are 0, there's no point in explicitly going through and multiplying this value times a 0, and this value times a 0, and this value times a 0, because we know the answer is going to be 0 regardless of what these values are. So we don't need to do that multiplication. And that's what, when you have sparse matrix functionality built into the given software that you're using, the matrices are going to be stored without storing all these zeros, and the computations are going to be done without doing any of these additions or multiplications by values that are 0. So we can basically reduce the number of computations down quite a bit. So if we actually, just as a, again as a toy illustration, here I'm creating a matrix that's 10,000 by 10,000. And I'm sparsifying it by just setting everything that's bigger than -2 to 0. So this should be about 2.5% of the observations should be non-zero. There's a package in R called SPAM, which stands for Sparse Matrix. There's also one called Matrix with a capital M that also has sparse matrix functionality. And essentially any software that is built to deal with numerical calculations well will have some functionality for dealing with sparse matrices. So Python does, MATLAB does, a lot of other packages will. So here I'm basically saying, okay, take that original matrix and convert it to a sparse format. I think we'll probably end up talking about this, what the sparse format actually looks like a little bit in the linear algebra unit, but I'm not going to go into that now. And I can print out what are the sizes of the objects, either the original matrix, so this guy here, or the sparse matrix, so that guy here. And you can see we've gone from about 800 megabytes to about 26 megabytes. So that's quite a bit of savings in terms of space. And then I'm just going to go ahead and do a matrix multiply of that matrix times a dense vector. So this vector itself doesn't have non-zero, it doesn't have zeros in it, but the matrix that we're multiplying does. And if I just use system.time to do that, we can see that in this case I get about a 40-fold speed up between doing it with the original dense matrix that has all the zeros explicitly in it and doing it with the sparse matrix where we're not storing the zeros, nor are we doing any of the computations with the zeros. So it can make a really big difference and basically allow you to do operations in a very small amount of time that if you were trying to work with the dense matrix would essentially be infeasible to actually carry out. Okay, the next thing I mention here is, and I think I won't bother going through this in any particular detail, but there's been a lot of work in the last few years on thinking about how to deal with computations with big data sets. And some of the ideas that one can think about in terms of dealing with this are actually using statistical concepts. And part of the motivation here is if I have a very big data set, I may, if I use all of the data set, I may have very high precision in calculating whatever quantity is that I'm interested in calculating. Well, I may not need to actually use all the data set to get a sufficiently accurate estimate of whatever quantity is that I'm interested in. I could do statistical sampling of some sort and use the kinds of ideas that we know about from statistics to bound my errors, to bound my uncertainty or bound my error from having used a subsample from the full set. So we can actually use statistical concepts to deal with computational problems. Which is sort of the reverse of the way we've been thinking about things, where we've been thinking about using computations to deal with statistical problems. Here we're thinking about, in some sense, we're sort of turning that around and putting it on the other foot. So there are a couple sort of specific ideas in here about how one might do that in practice. And I will let you read that on your own. And then the last thing I was going to mention is a little bit about Hadoop and the Mapreduce paradigm. And I didn't actually sort of implement any of this in reality, so that I don't have the. Usually it's a good idea because it provides a little more rigor in terms of presenting the material and actually seeing it in action. But actually implementing Hadoop on a system involves a fair amount of systems administration. So we have sort of a toy Hadoop setup working on the SCF. But for various reasons, it wasn't quite working to use that to work through a demo here. So I'm just going to try and give you a flavor of what happens with Mapreduce. And the basic idea is that you have a very large data set, and you are not able to even store all of that data on one single machine. So you need to spread it out across multiple machines. You may have tens of terabytes or petabytes of data. You can't get a single disk drive that will actually hold all the data. So you need to distribute the data across multiple machines. And if you were to then try and do all the calculations where you read from any of those individual disk drives, transferred the data to one place where you're doing the computations, and then stored the result, that would essentially take infinite time because you'd be having to transfer all that information over the network. So one of the notions behind Hadoop and Mapreduce is that you are actually trying to do the computations as much as possible in a distributed fashion and have the data be sitting in a distributed fashion. So the idea is to set up an infrastructure that would allow you to do the storage and the computation in chunks distributed across a network of machines. So one way to think about sort of the basic steps of this is that in a distributed fashion, you would basically read in individual data objects, and depending on what the data was, this could take different forms, but individual chunks of data. And then with each of those chunks, the idea is you take those inputs and you create key value pairs. So you're basically stratifying the data in some way. And so for each sort of unit of information, and we'll see a slightly more specific example in a minute, we're going to create a key for that, and then we're going to have a value associated with that. So we're basically grouping all of our data by different keys. So if we were doing stratified analysis, this could be grouping by people of different ages, or it could be grouping by people of different countries, or any sort of grouping that you could imagine, where the keys indicate what the grouping is. And then the idea is, so that's the map step. And then the reduce step is basically for each key, so for each group, I'm then going to do some calculation, some aggregation or summarization or some sort of estimation. And then I'm going to write out the result of that. So the result of that is going to be a pair that's the key, and then the result from having done some calculation on all the values from here that are associated with that key. So that's the basic idea. And then Hadoop is basically an infrastructure for enabling and implementing this sort of paradigm across a network of machines. And it comes with a distributed file system that manages the breaking up of the data into different files that are distributed across different machines. Okay, so I know that was a bit vague, but are there questions at this point? Okay, another thing I'll mention that's built in here is once you get to having, and this was sort of what Google realized 10 or 15 years ago, is that they could buy cheap hardware, and as long as they built in redundancy and were careful about checking when machines weren't working, they didn't need to have machines that were really reliable if they were distributing calculations across many machines. If one machine stops responding, as long as you know what tasks were sent to that machine, you can just send those tasks to some new machine once you realize that machine is no longer responding. So there's robustness also built into this framework, that you're sort of monitoring the tasks as they go along. If a task doesn't come back from a machine, you're not able to get the results back. You just repeat that calculation on some other machine. Okay, so Hadoop is based on Java. If you were using Hadoop, you could do the coding in Java. There are some packages in R and projects in R that allow you to interact with Hadoop. There's something called R Hadoop, and there's also something called Repe, I think is how the folks are pronouncing it. So let's see a little bit more of sort of what the flavor of algorithms might look like if you were in this context. So the basic example that you would see if you looked in Wikipedia for Mapreduce is basically a word counting example. And so suppose you were dealing with a very large body of text data. You can sort of see where this all comes from, since this is this all came out of Google back in the day, and so obviously counting words is something that they do a lot of. So here's sort of pseudocode of what a map function might look like. So suppose the inputs are documents, and you basically want to count words in this data set. Well, as the input to the map function, I basically have a key value pair that's the name of the document, and then the actual string that has all the words in the document. So my map function in this case would operate on each of these, where this is basically specifying a chunk of data. And then you can imagine these chunks of data are stored in a distributed fashion across all the various machines. And then what I'm going to do is I'm going to, for every word in the document, this function is going to return back out. So there's some sort of for loop here. The word, and that's the key at this point, and just a 1 to say I found one of these words. So you can imagine doing this in different ways and sort of counting out the words in the document. But one way you could do this is just every time you see a word, spit out that word as the key and the value of 1 as the value for the key value pair. So I now have tons and tons and tons of these key value pairs floating around. I have the word identifier, and then I have this count of 1. And so the idea is then in the reduce step, I'm going to go ahead and do the counting. So the reduce step will now take in the key, which is now the word, identifier of the actual explicit word. And then this is basically going to be the set of all the values associated with this word. So for the word, whatever, classroom, there would be a whole set of different ones from the result of the map function. And I'm going to get, say, a vector of those ones, however many ones there are representing however many instances of classroom were in all those text documents. And so, I can just basically do the map step. The reduce step is, pretty straightforward here. I'm just summing up, I'm iterating through the values in this object, and I'm adding to my sum, and that's just going to count up the number of words. And then I'm going to return back the key, which is still the word identifier, and then that sum that I created. So the reduce step can be a lot more, could be a lot more complicated. It could be whatever analysis I want to do, as long as I can do it in the stratified fashion where I'm doing an analysis that's just focused on each of the values that are specific to a given key, and not trying to do something that goes across the different groupings. So here's another example where now suppose I have, and this is somewhat more realistic. This is actually what the code would look like if you were using R Hadoop. Suppose I have a very large collection of CSVs, and those CSVs have basically census type information. They have each row is information on an individual person, and then we have some sort of demographic information. So that might be income or age or any of these sorts of things. So here's what that would look like more or less using R Hadoop, but without actually having done it. So there's this RMR package that's part of the R Hadoop project. And we need to make a map function and a reduce function that are actually R functions. So here's the map function that I created called mymap. And that is basically going to take in an individual line of data. So presumably, what needs to happen behind the scenes here is there needs to be some preparatory work on the part of the package to basically be working through the CSV line by line and sending lines of the CSV into my map function. So the line is going to come in as v, and there's going to be some key value, some key associated with that line. So these are the individual lines of data that are the chunks in this case. And suppose that I've written some sort of function called myReadLine that will basically take this CSV line and do the parsing to pull out the fields of the line. So you guys have already done that. You could easily imagine writing that function as long as you know what the format of the line is. And now I'm going to create a key value pair as just taking out of the record, I'm going to take, for example, the state, and I'm going to take the income of the person. So suppose I'm trying to summarize income by state in this case. And there's this function that's part of the package called keyval that's going to basically take what I give as a key and what I give as a value and create this key value pair in some sort of object representation that is consistent with the guts of the package. Okay, and then I need to write a reduce function that will take, again, the key value, the key, and now v is going to represent the whole collection of all the values for a given key. So in this case, if I did it like this, k is going to be an individual state, and v is going to be the whole vector of incomes for all the people who live in that particular state. So I could, for example, do another quite simple reduce function could be to get the length of v, so it's just going to count up the number of people, take the mean and the standard deviation of v. Actually, retrospectively, I should have used median in this case, and some sort of more robust estimate of the variation. But again, I'm going to use this keyval function to basically now I'm producing a key value pair that's the state, and then the summary information specific to that state. Okay, so any questions? And then the way you actually use Mapreduce in the R Hadoop package is you basically use this Mapreduce function. You give it a name that basically refers to that collection of CSV files. You give it your map function, you give it your reduce function, combine is another sort of set of operations that you can do within this context that I won't go into. And you're telling it, okay, the inputs are CSVs and create CSV files as the output. And so that would actually go through and churn through and do all these calculations. And then if you wanted to see what the actual results were, there's a from DFS, so from the distributed file system function, that will take the output, the object that is representing the output here, and should return it back. So I think this would return it back in the form of an R data frame. So that should give you the summary information on income. So that's a pretty quick overview of that, but just to give you sort of a flavor of what Mapreduce is doing, and if you start to run into big data problems, you could start to think about whether this is a paradigm that would be able to address your particular problem. And you can do more, more complicated, more sophisticated things that I've done here. When we're doing the mapping, for example, we don't need to, we could throw out data. We don't need to pass along key value pairs for all of the data that we read in. You can produce multiple records from any given observation or chunk of data that you read in. But basically, the main constraints are that when we're doing the mapping, each of the records that is read in needs to be treated independently from other records that are fed in. And when we're doing the reduce step, each chunk of data associated with a given key needs to be analyzed independently of the data associated with another key. And you can imagine that by virtue of the kind of paradigm that this is operating under, why these constraints are needed, because we're trying to do this in a distributed parallel fashion. There needs to be some sense in which we're breaking up the data and breaking up the computations and not having communication across the different pieces. Okay, so any questions before we skip on to the next unit? Yeah.
So in your last example, you asked him to calculate SD. So is it done automatically in a parallel fashion, or collect all the...
Yeah, that's a good question. I suspect that any given reduction step is going to be done in a serial fashion, and that the parallelization is only over the different keys. But I don't know, for example, particularly if you're just using Hadoop without all the R stuff on top of it, whether, say, the Java code is written in such a way that some of the individual calculations in any individual summarization for a specific key, whether any of that would be parallelized. But yeah, you could imagine that if you end up having a relatively small number of keys and a very large analysis done on any given key, that if it's not parallelized, it could get to be quite slow. Is anybody more familiar with this than I might be who has any thought about that? Okay. Other questions? Okay, so let's move on to the next unit. So we're going to talk about numbers on a computer. So this, this is it's sort of a funny unit, because we're going to be talking about, in some ways, sort of fairly basic sorts of things, like what happens when you multiply two numbers together. But it's information that a lot of people don't realize when they're using a computer, and it can come back to bite you in a lot of contexts unless you know what's going on. So it helps to actually have a fairly detailed understanding of how numbers are handled on a computer and how they're represented on a computer, so that we know what to be concerned about and what will work and what won't work. Okay, so we're going to start talking about just storing an individual number on a machine. So if you think about how a computer stores things, it stores things in bits, 0, 1 flags. So a bit is basically just a switch that you can turn off or you can turn on. So it can basically represent a 0 or a 1, and so therefore we're naturally going to be representing things in base 2, because everything's represented in terms of these on-offs. So when we take a collection of 8 bits, that makes up a byte, and that's going to be sort of our fundamental unit of information. So for example, when we were talking a little bit about different file encodings and ASCII characters, there are 128 different ASCII characters, and those include, the various things like end of lines as well as actual A, B, C, 0, 1, 2, 3, etc. So 128 is not an accident. It's 2 to the power 7, and so these ASCII characters can be stored in 7 bits by taking 0, 1 and raising two possibilities, raising that to the power of 7. Another comment about thinking about bytes is one of the reasons that hexadecimal, that base 16 is handy, is we can basically go between base 2 and base 16 fairly easily, because 16 is a power of 2. And yet we can write, if we started writing out numbers as 0, 1, 1, 0, 0, 1, it starts to be, kind of tedious and a little bit hard to sort of see, is this number different than that number? All I see is a bunch of zeros and ones. So one way to represent a byte is basically represented as 2 base 16 numbers. So with 8 bits, we can represent 256 different pieces of different unique values. And that is also 16 raised to the power of 2. So any given base 16 number can represent, we can use 2 base 16 numbers. For example, 3e is a base 16 number, or a0 or ba. And that can represent the same information as we can write out as a sequence of 16 zeros and ones. But, it's easier to remember 3e than to remember 0, 0, 0, 1, 0, 1, 0, etc. Okay. So if you think about what a file format really is, it's just basically a way of taking the bits and bytes that are sitting on the computer on disk and interpreting what those things actually mean in terms of sort of human interpretation of those values. Okay, so questions at this point? Okay, so let's think about storing an integer in terms of bytes. So if we have 2 bytes, then we have 16 bits because we have 8 bits per byte. So I could think about if I were going to store an integer using 2 bytes, I can think about how many unique integers I can represent. So I have 16 bits available to me. Each of them can take any of 2 values. So I can represent 2 to the 16 different unique values with 2 bytes. So if I had a 2-byte representation of an integer, I can store 65,535 I can store any value. Suppose I was starting with 0, I can store any value from 0 up to 2 to the 16th minus 1. Minus 1 taking account of the fact that I also want to be able to represent a 0. So if I only had positive or non-negative integers, I could store the largest integer I could store is 65,535. On the other hand, in general, we want to be able to work with both positive and negative integers, so I need to take half of those possible values and throw on the other side of the 0. And so therefore, I can basically represent plus or minus 32,767 if I were using 2 bytes to represent any individual integer. Okay, so that starts to show us that there are going to be limits in terms of if we want to be fairly efficient about memory use and not use too many bytes for any given number, there are going to be limits in terms of how large a number I can actually store and manipulate on the computer. Okay, so we can already start to see that there are going to be implications of this when we actually use software. So let's go ahead and see that, just a basic example of that in R. So I'm going to create an integer a by actually enforcing that it be an integer and not a decimal value. Okay, so here's a. And now if I try and multiply a by itself, all of a sudden I can't do it. So this is not, it's a sort of big number, but it's only, 3 million. It's not a particularly large number. And yet when I try and multiply 3 million by itself, all of a sudden R says, nope, sorry, I can't handle that. And the error message it gets is informative. It says there's integer overflow. So the overflow means you're trying to work with a number that's too big for me to store in my representation of how this particular kind of number is stored on the system. If we hadn't converted this to an integer, we would be able to do this calculation and get back that this is, however many, whatever the result is, and we'll see why in a little bit. Okay, so so that sort of takes us to thinking about, well, what about how would we actually store real values, decimal numbers? And so real numbers also go by the term of floating points, and in the old days, sometimes they were stored using 4 bytes, so those are called single precision floating points. These days, essentially, all decimal values are stored using 8 bytes, and so 8 is double 4, so these things are called double precision floating points are doubles. And you've heard me use the term double and double precision a few times, I think, and floating points too, for that matter. And that's where this terminology comes from. So let's actually go and see if we can start to sort of ferret out what's going on behind the scenes when things are being stored and manipulated in R. So I'm going to make some vectors that are 100,000 long, and then we're going to try and see how big are they in terms of how much memory do they take up in R. So I'm going to first create a vector of random normal, so those are going to be stored as double precision floating points. Then I'm going to create a vector of integers, so the colon operator, as we've seen, produces integers as outputs instead of decimal numbers. And then I'll create a vector of characters. And we'll see what happens with those guys. Okay, so now if I ask how big these guys are, each of these was 100,000 values, and I just said, okay, a double precision takes 8 bytes per value. So we see this more or less works out. This is 100,000 values times 8. Indeed, that would be 800,000 bytes. And if we look at y, which is integers, it says, oh, that's 400,000 bytes. So that suggests that each of these integers is taking up 4 bytes for each integer. So here I said, well, what if we stored integers in a 2-byte representation? Well, this tells us that R is doing something that will store somewhat bigger values than that. It's actually using 4 bytes per integer. Any thoughts on why there's this 40 sort of lurking here in the number? Right.
It's like overhead is storing the node on space or something.
Yeah, there's some sort of overhead in terms of associating the object with a name and things like that, and sort of representing metadata about the object. So when you look at these things, you'll generally see that there's a little bit left over that's added on top of what you might expect if you actually did the calculations, that it should be exactly 800,000 bytes. So if we look at character strings, it's interesting. We can see, oh, okay, so this z, which is the same length as the vector of doubles, is also being stored, it seems like, as 8 bytes per value. Any thoughts as to what could get more funky with character strings that we might need to think about in this case? What's going to be a fly in the works here if we think about trying to pin down how many bytes are used for any given string?
Along the string.
Yeah, so a string is essentially arbitrarily long. Like if I think of making a single scalar string in R, obviously that's going to be a character vector of length 1, but that could be the letter A, or it could be 7 billion characters all strung together. So obviously that can't all be stored in the same amount of memory. And I don't, so here, it seems like it's somehow using 8 bytes for each of these values A, which seems like quite a bit, right? We already said that if we had an ASCII character, we can store that in 7 bits, which is more or less 1 byte, and yet here we're seeing that it's actually storing it seemingly in 8 bytes, so seemingly 8 times as much as we might think we need. And it's interesting, if we do, if we start doing this, and we do this, we can do the same thing. And it doesn't really seem to have changed very much. So I don't actually know what's going on here. Does anybody have any suspicions off the top of their head? No, I think I was toying with the idea of putting this on as an extra credit problem on the problem set. So you might see this as an extra credit problem to you could try and go ferret out what's going on here and how R is actually storing these character strings and dealing with the fact that any given string can be essentially arbitrarily long.
Does it possible that R actually allocates more memory location than needed for a string in case you just want to append it?
Yeah, I mean, I guess that sort of gets back to this question of what would happen if we have a character vector, and then suppose one element, I take that and I try and replace that element. It may want to have an extra buffer to be able to do that without having to allocate that whole character vector in memory again. And I guess that also then gets to the question, how are these things stored in memory? Are they stored contiguously, one after another, or are they stored in some other representation? So I think, in order to really understand that, we have to delve into all of these questions that relate to some of the various topics that we've seen already in class. Okay, so I think I'll leave that as a little bit of an open mystery. for our purposes, it's probably not a critical mystery because we're mostly going to be working with numbers and thinking about memory use and what kinds of sizes of magnitudes of numbers we can work with. Okay, so we can, as we've already seen, we can calculate how many megabytes of memory or well, I guess that sort of depends on what the file format is, but so let's stick with memory. We can calculate how many megabytes of memory a given object is going to take up, depending on how many elements there are in there, and in this case, assuming that this is a double, that the elements are just regular numbers that we're storing. So we can just multiply it by 8, divide by 10 to the 6 to convert from bytes to megabytes, and that's going to give us an initial estimate of how large an object will be. Even more roughly, we could just divide by 10 to the 5th, or we could just take the number of elements and multiply by 10, and that will give us the number of megabytes that an object will take up. So roughly speaking, if we had 10 million elements, that's going to take up about 100 megabytes. If we had 100 million objects, that's going to take up about a gigabyte, and that's just based on sort of working with orders of magnitude here. Okay, so one object in R that's quite useful for when we're dealing with these properties of numbers stored on the machine is a special object called dot machine. The dot is because it's sort of a hidden object that is sort of a system level kind of thing. So if we go back to R, we can type in dot machine and see what it says. And we can see it has a lot of things that relate to sizes of numbers and how big things are. So size of a long, size of a pointer, min and max things, et cetera, et cetera. And we're going to see a variety of these different values as we work our way through this unit. So one of them, ones that we could that we might look at is dot machine. So this thing is a list, integer dot max. So that says that the maximum integer can be stored is 2 billion, it looks like. So if we actually calculated 2 to the 31st, indeed that's essentially that same value. So remember when we were thinking about 2-byte values, we said we can go between plus or minus 32,767. This is, so if I had 32 here, that would be 4 bytes. Half of those are going to be allocated to the negative part of the real line and half to the positive part of the real line. So that's real line. So that's why I'm doing 2 to the 31st because instead of 2 to the 32nd. So 32 is 8 bits times 4 bytes. And that would be then tells us that indeed R, we've already seen this, R is storing integers in 4 bytes, and it makes sense that this is the maximum value we can store, given that that is, given that things are stored as 2 bytes. And so indeed, if I do 21474836647L to enforce that it should be an integer, it says, okay, I can work with that. If I do this, it says, nope, I can't handle that as an integer. And in this case, R says, you know what I'm going to do? I'm going to convert that to a floating point value and work with it as a floating point value instead of explicitly as an integer, because of the fact that this guy would be too big for the machine to handle with 4 bytes in terms of it being an integer. Okay, so I'm going to leave you with a little bit of a dilemma, and we'll resolve the dilemma next time. So. So I won't tell you what this is, but I'm setting this back to the default. This is basically the default for how many digits to represent in spitting back the answer, in printing out numbers. So if I actually do this calculation, it says the difference between 0.3 and 0.2 is not 0.1. And yet if I just print out the values 0.3, 0.2, and 0.1, it says, yep, 0.3, 0.2, 0.1. So I will leave you with the disturbing possibility that R is fundamentally broken. And we'll see that it's not next time.
Okay.
Yeah, hold on one second.